Welcome everybody to this third session about deep mitigation. I think we have two very nice presentations here. First by Iñigo about global energy transition and especially looking at the material requirements for electricity. The second one is by Alexander GOLUB about the feasibility of 100% solar and the wind energy system for Russia. Iñigo, can you share your screen? Then I'll give the floor to you.
Okay, so good morning, afternoon, everybody, depending on where you are. So it's a pleasure for me to present you the work we are doing in the modeling team about the modeling of the electric grid in an integrated assessment model we are developing. So I'm going also to present some preliminary results, but I want to stress that this is ongoing work. Okay, so we are developing a new integrated assessment model within this H2020 project, which is named Locomotion, where we have many partners. Here, most of the work has been done by the University of Valladolid. So the main motivation to model electric grids, I mean, there are several motivations or several reasons. So one of the reasons is that there is a general consensus that the transition to renewables is going to imply a certain degree of electrification, further electrification of the economy. Also, the wind and solar resources are spread through the territory, so we will need to build grids to reach the good places. Also, there is these interconnections between different regions or different countries, which are assessed as being one of the most relevant options to deal with the issue of variability of renewables. And then last but not least, we have still many people in the world who do not have access to electricity. So in the context of sustainability and SDGs policy measures, if these people are going to reach electricity, we will need to expand the grid until then. So in the context of the model, what is important that the modeling of the electricity network is important, of course, for the energy part, but it will imply monetary investments and also material investments. So I'm going to explain more about this. A very quick literature review showed us that, in fact, very little work has been done up to date about this topic. And here I copy a couple of studies which are from this same year, which have focused on the electric grids, but where we can see some of the things I already pointed out, that this trend of increasing importance on length of electric grids and depending on the amounts of storage or the generation technologies that we have in our mix. But in general, this is a very understudied topic. So very quickly, I wanted to give a glimpse about what is the model we are developing, which we have called William within limits in IAM. So here you can see different boxes. So as it is typically in IAMs, we are trying to connect different dimensions. Maybe if I have to point out something, I will point out that we are introducing some dimensions which are rarely taken into account. For example, here in economy, I'm not sure if you can see my mouse, but we have put economy and finance. So we are going to research also about how we can finance the transition. And then we have here a module about population and society, where we are going also to try to compute different indicators about well-being, inequality, employment, etc. And then also maybe another novelty or original feature of this model is that we have a strong focus on materials. So we have a module for accounting especially the materials required with the energy transition. And one challenge in this work is to achieve the consistency between monetary and the physical dimensions, because we have a very developed economy module. So why these electric grids usually are not taken into account into IAMs? I think because the challenges are very big, very important. Any detailed analysis of grids requires power flow analysis, which is beyond the scope of integrated assessment models. Then we have the complexity of the interaction with the management options for the variability of renewables. And then we have this problem with or this issue with the potentials. So here in our model, we are taking a very pragmatic approach. So the general idea is to have a very stylized representation in terms of energy, let's say, but that is going to allow us to connect this additional electric grids with different modules of the model. Particularly, I already mentioned materials, economy, and also the climate change impacts and adaptation, which for electric grids seem quite important. So what we have done, in fact, we have taken as a starting point the work I mentioned before about applying image, Dittmann et al., which in fact they also take a very pragmatic approach, which we liked, which is just to take today how many generation capacity we have, and then we index this growth in generation capacity with relation to the current length of the grid of high voltage, sorry. We do a little something a bit different because we add a factor here, this one minus des, which is decentralized, or if you want distributed generation, to account for the fact that if we generate energy in the same place and we consume it, then we don't need so much high voltage grids. So let's say it's a correction of the initial formula. How do we integrate this in the model? Of course, now I don't have the time to explain you in detail, but basically we have here the three elements I mentioned: energy, economy, and materials. So basically we estimate, following this formula, an amount of high voltage grids. Also, we take into account the penetration of renewables, and we take into account that variable renewables may, if they increase a lot, they may have consequences in terms of higher curtailment in the system, etc. So with that, we compute the amount of grids, and we have a very large technological disaggregation in which we have high voltage, medium voltage, low voltage, underground, aerial, etc. So we have here all these subscripts. And then for each type of grid, we compute the material requirements, we compute the costs, and we compute the full power flow, the full material flow analysis. Okay, so this is something I mentioned maybe too fast in the previous slide. The fact is that we are taking into account that depending on the variability, the options to deal with the variability of renewables, for example, how much storage capacity or this capacity of interconnection, we have derived a regression from another study to take into account how much curtailment will the system will require. So this is integrated also in the model. So some quick results. This is the kind of data that we have been looking for. No? So we have kilograms per meter per type of grid. So we have, of course, bulk materials such as concrete and steel and aluminium represent the most of the part in terms of weight. But then you can see that there is a very big variation, a very big amount of different materials which are also used and which we compute in the model. Okay, so I mentioned that this is for the ongoing work, but I'm going to show you some explorative results running 3 scenarios. So one scenario is a typical business as usual, and then we have 2 green growth. One in which we have the default options for grids, which I'm now going to explain, and another one in which we explore what will be the implications of improving factors so the required grids will be lower. So what are we going to do? For example, in the green growth plus, we are going to take into account this factor which I showed you, in which we reduce the amount of grids if we have distributed generation. Then another thing we are going to do is to double the capacity of interconnection to see what happens. And then in the third option, we are going to replace copper by aluminium, because copper, as you probably know, most of you, is it's assessed to be critical in the future. So we introduce a policy to replace copper by aluminium, which is more abundant. Okay, let's see what.
Sorry, Iñigo, can you wrap up in about 1 or 2 minutes?
2 minutes left.
Yes.
Okay, thank you. Okay, so some results in terms of here on the left-hand side, we have, I'm running until 2060, and we can see that the green growth scenarios, which are the green and red, are here reaching 100% electricity in 2040, and the business as usual, which is the blue line in the figures, is lagging behind. Okay, in terms of capacity factor of the whole system, we can see that due to the increase in renewable generation, the capacity factor decreases very fast from current levels. So this has implications in terms of grids, because we need more capacity to produce the same energy, but we still need grids to transport the electricity when it is produced. Okay, so here in this side, we can see the total high voltage grids in use. So we can see that in the green growth scenarios, we multiply by 2 or 3 times the amount of grids. This is partially due to the introduction of renewables and partially due to the increase in the consumption of electricity. Okay, and then in terms of materials, these are logarithmic figures. So take that into account, and you can see that we have compared the cumulative extraction of materials required for grids over time with relation to reserves here in the left-hand side and to resource in the right-hand side. So some comments here, because there are many lines, but some highlights will be that zinc is the most critical. You can see here that it approximates almost 1 in 2060. And copper also, we can see that it approaches around 10% of current reserves by 2030. So this is without accounting that the rest of the economy, of course, is going to require copper, but we can see that grids will require a significant amount of the reserves. Okay, so with this, I can conclude my presentation saying that electric grids are a key component of the energy system, which is often not included in EAMS due to its complexity. So here we have proposed a stylized methodology to focus on the interconnections with the materials, economy, and climate change impacts and adaptation modules. And in fact, when we run the model, we see that in transition scenarios, a significant increase in grid length, driving important monetary and material investments. So about further work, just 4 points which we want to explore in the future, and I will be glad to hear more ideas later. So the idea is that I didn't mention, I think that this we are running with a global model, so it will be very nice to have country-specific parameters for William, because William is going to be a multi-regional model. Then we have to improve this representation of the transmission lines. We would like to endogenize the estimation of electric grid losses, and maybe also to expand to represent the smart grids technologies. So thank you very much. That's all from my side.
Thank you, Iñigo. It's really impressive work. I think very important as well. And I would propose to go straight forward now to the second presentation by Alexander.
Thank you so much, and good morning and good afternoon, depends what time zone you are in. And so it's kind of a rare occasion for me to represent the Russian Academy of National Economy. But I do some research with my colleagues Vladimir Potashnikov and Michael Brody. He also co-authored that presentation. And this work was done with support of a Russian Science Foundation. Well, motivations. It's kind of clear that Russia needs to be part of the global process of transition to zero carbon economy. And sooner or later, Russia needs to be on decarbonization pathway. And the World Bank study just published a year ago clearly showed that Russia on the long run is better off to participate in coordinated climate policy. And this participation will require quite a significant diversification of the Russian economy. But transition pathway poses two major challenges for Russia. On one hand, Russia needs to spend a lot of resources to decarbonize the economy, and on another hand, because changes on the global carbon market, disruptive technological innovations, Russia will lose rent revenues from export of natural resources, first of all, fossil fuel resources. Well, what could be response to this challenge? And we just try to construct maybe a little bit marginal and provocative scenario that Russia goes 100% to renewables by 2050, and first of all, wind and solar. And of course, this would solve the first challenge, how to decarbonize the economy. It wouldn't solve second challenge, what would be a substitute for losses of resource rent. Then we realize that maybe the best way for Russia to decarbonize the economy, not to try to match precisely demand and supply, because most alternative energy has a lot of advantages. One big disadvantage is that random character of production of renewables. So you need to have storage, you need to engineer demand for electricity in order to meet demand and supply. And we decided to consider a completely different scenario, just to produce much more energy than critical demand, and use the balance to produce hydrogen, and use hydrogen as a substitute. The export of hydrogen will be substitute for losses in export of fossil fuels. The model was well, old model, but in a new format. Was programmed in R, and which makes quite easier to operate with this model. And it's a combination of two models. One is quite a granular model that computes balance in real time, balances supply and demand, and we run that for the end of the period for 2050, when you have the worst case scenario in terms of balancing of energy supply and demand. You have almost 100% renewables by that time. And then when you have this balance, then you run conventional times model, and you just compute transition pathway. And we consider several scenarios, and around 100 different scenarios of final composition of energy mix, and run optimization across them, or I would say robust optimization. And then we also for each of those scenarios, we compute optimal transition to zero carbon emissions. Well, and indeed, Russia has vast potential for wind and for solar energy. And we analyzing this potential, we concluded that the way for Russia to go is primarily with wind energy, because solar potential is kind of in conflict with agricultural use. Best agricultural land and solar potentials are pretty much in the same area. Well, that's how it's gonna look like. You can see here quite substantial increase in energy and power production. By 2050, it's about 6 to 10 times. We try different scenarios relative to this this current demand, and on contrary to all existing literature that try to model simultaneously energy efficiency, saving of energy, and so on, we included that. Don't take me wrong, we included that option, but not to reduce total demand, just to reduce critical demand, and we must meet a certain amount of consumption. Well, and then rest will be transferred into hydrogen. And of course, hydrogen, most of this hydrogen would go to export. And a model could be quite granular, but at that point we have 9 major regions, and you can see here, like for example, this region. So that's how much you produce, and then what is used. It's for use, and then it is rest goes to hydrogen production. Like lowest layer is hydrogen. Of course, we also consider transmission of power among regions. I don't have time to show that. Well, and that's how final consumption looks like, and you have hydrogen is shown here below that. So we still have quite a bit of nuclear energy, and in further scenarios we are considering to save some of capacities running on natural gas and offsetting remaining emissions using nature-based solutions, just considering high quality, high integrity offsets. That could be, Russia has plentiful potential to plant forest on agricultural land, and it's not a problem to offset emissions. So what is the main challenge for Russia to navigate this transition? And I wouldn't talk about political aspects and lobbying of oil, gas, and coal industry. I just look from point of view of investment. And here's a kind of annualized investment calculated using different cost of capital. And you can see that by 2050, it could be quite substantial, but if you compare that investment with what is invested now into exploration of natural resources, well, it's kind of comparable. Also, what I'd like to stress here, that cost of transition depends a lot from cost of capital. And you see this line, 10% cost of capital. And we run scenarios with even higher cost of capital. So basically, Russia needs to overcome investment risks and need to improve investment climate. And again, I don't want to go into political discussion, but Russia needs to figure out how to be better integrated into the global economy, and how to ensure that investment climate is good. And alternative energy, what is good about alternative energy? It's very scalable and basically and divisible. You can you have some investment, you put that into operation and so on. So you don't need to commit quite huge investment program right away. You can invest and learn. And raw materials, and I appreciate previous presentation, and constraint on raw materials might be important aspect to consider. But for Russia, with abundant raw materials, I think it shouldn't be a problem. Most importantly, fresh water. Fresh water is available, especially in places where Russia has the highest potential for wind energy production. It could be converted into hydrogen. As I said before, high investment risk is a major problem and could be potentially a major barrier. Well, this work is in progress, and as I said, we are considering a few extensions, for example, to use natural gas, have that as a reserve capacities and offset residual emissions by using nature-based solution. And also we are considering to combine this model with CG model, but CG model that would not only kind of traditionally replicate gradual transition of the Russian economy, but excess of energy could be used to produce hydrogen, but also could be used to organize production based on energy intensive technologies like 3D printing and robotics and so on. So in the future, we need to consider kind of transformation, deep transformation of the Russian economy beyond the energy sector, just given the fact that that might be quite a significant supply of power supply, and if Russia using hydrogen production and using 3D printing and robotics will create flexible demand for electricity, then it might be the way of transition. Thank you, and I think I need to stop here.
Thank you, Alexander, for this very nice presentation. Okay, let me quickly just ask this question by Robin Lembel. Will the distribution of wind power in Russia significantly change depending on the degree of climate change? Did you actually have a look at it?
No, we use NASA data, historical data, and indeed one of extension is to use Cordex data and see what could be the difference in energy, especially, well, solar energy, it's less concerning, but wind energy, it might be some changes.